Okay, so this course is partial differential equations in applications. So I'm an applied mathematician. My problems, research problems, are always physically motivated, and the hypotheses I use in the problems are not for technical reasons. In PDEs, one do use hypotheses which are for technical reasons. There's no problem with that. That's important, right? To prove theorems, to do advanced techniques, and so on. But here in particular, things are going to be physically motivated, and of course, trying to understand new things about partial differential equations, how to deduce new partial differential equations, and that's the idea of modeling, right? Deducing, putting a mathematical problem in a correct perspective so you can solve it in an approximate way, right? And in particular, to see solutions. So the idea of this course, I wrote this and this is how we're going to start. We're going to start today, which I call geometrical theory for waves. It will start at one point more with hyperbolic equations, okay? I will not do the course on purpose. I will not do the course as a standard courses in PDEs, that it's like that in undergraduate courses, but also in graduate course, which is hyperbolic equations, elliptic equations, Laplace, and heat equations, diffusion equations, right, as another parabolic classes. No, I'm going to start with actually an abstract formulation of theoretical theory for waves. I work with waves, and I think this abstract theory in the beginning, you won't not see applications right at the start. It's very good because it builds up a nice intuition in our head of how mathematically things related to waves behave. And then I'll give you an example with waves, okay? And then we'll go, I intend to do things with singular solutions. And I'll do a little contrast between, let me call it, modeling and distributions. So it's going to be more on this side. I'll mention a little bit about distributions, but the course really where distributions are treated in a functional analytical way, Sobolev spaces, here at IMPA, is a course called PDE's linear theory, Teoria linear, okay? So I'll just mention this earlier, but I'm going to look at singular aspects of solutions from a modeling point of view, a more constructive, where you see things, right? Than in the sense of distributions. And I want to do some asymptotics of differential operators, which has to do also with modeling. So this modeling here is, I put like this, which is the emphasis, but this also has to do with modeling, right? Writing in a, as I call it, as in an educated way, getting from a complicated system of PDEs, a simplified system of PDEs, having the application in perspective and correct things about differential equations in our minds too. So this we'll see. And as I told you before, and now maybe it's good recording, in Brazil, in Latin America, we have excellent people, excellent research in PDEs, which is mostly from the functional analysis, right, point of view. Functional analysis, spectral theory, and so on, right, point of view. Here, it's kind of a different perspective, and as you'll see, but it's of course, an applied math look at it. So we'll see things, I think, that are not typically seen in math courses in PDEs. So one thing I want to talk about, which I like, is multi-scale, so not only asymptotics, but multi-scale analysis. I'll give you an example. Multi-scale analysis. When I talk about Laplace equation, elliptic problems, I want to do it from an integral, because it's different, and there's very nice things, integral, boundary integral formulation. Okay, a boundary integral formulation, let me put it of Laplace's equation, right? So you rewrite the problem as a boundary integral, and many nice things arise. As part of this, I want to talk about Dirichlet-Neumann operators, which is a very useful thing, for example, in physical problems, but it's an object that arises from, say, a boundary integral formulation. And this is actually it's nice because it's a Fourier operator. It's a pseudo differential operator, right? And we'll see how to use it and how to construct it in certain situations. I will then talk about some diffusive problems. So that's how I start connecting hyperbolic problems, elliptic problems with parabolic problems, okay? And as I just mentioned to you, in terms of as, I will then do some advanced topics through advanced text, or research papers, which I might give you to read and write about, or in some of them I will discuss it myself as almost like a lecture mini seminar in some extent, like a slower seminar, right? A seminar with more details in the perspective of the course, because what I want you to see is what is all about partial differential equations and applications from the more academic introductory point of view, all the way to what can be done in a recent research paper, right? It's a doctoral course, so we can do that. I've done that, so I know it will work. I asked today for the library to put these books on reserve, okay, which are for you to consult in the library. You cannot take them home, right, when the books are on reserve. So let me write in a sort of if I write the whole thing here, it will take too much time. So just write a little bit the title in abbreviated form and the authors, okay? They will be at the library. So there's one that's basically PDEs. Fritz John, it's an older book that actually I used in my PhD. I think it's a very good book. It's thin, and you have to be careful because Fritz John starts telling you a story. It's all in words. I remember it was a very good exercise to write down in a mathematical language things he's saying to make sure you understand. But I think it's a very good book. One that's I think it's somehow a little bit inspired in Fritz John, but it's more recent, a little more recent. And it's expanded. It's a thick book, and it's called Partial Differential Equations of Applications. Is by Eric Zoder. Then another book is Nonlinear PDEs for Scientists and Engineers by Debneth. We have it here at IMPA. It's not my favorite. I have this book. It's not like a very good book to read. Some parts it is, but not for everything to study, to learn. But it's a very good overview of many types of equations to find things and applications. So it's not like a textbook, but it's a good book. Then let me mention this one. Let me put this cut here, which is partial differential equations, because I'm not really going to use it. But it's a book that's used in the course of PDE's linear theory. It's more into functional analysis. But so for those of you who want right, to look at already things, oh, André is mentioning this, but it's not, he's saying he's not going to do the analysis. It's a classic book, very good book by the American Mathematical Society, book by Evans, which, on the other hand, I think when he talks about applications, he mentions it a little bit and lets it go. So if you don't know what he's talking about, it's not very helpful. So it's a very good book, excellent book in the analysis, functional analytic point of view. Oh, and finally, which I should put here, because it's applications, and I will use it a little bit. It's an excellent book. Not so easy to read at some parts in the beginning. It's a classic by Witham. Okay, so at some points I'll refer to Witham's book. It's a classic, 1974, and until today, papers and waves that need to mention a book, it's Witham's book. It's very written. Some parts are dense in the sense that if you haven't studied a little more introductory part, it's not that easy to read, but it's an excellent book. It's really very, very, very good. And finally, oh yeah, I cannot forget, there's going to be my notes. I have in Portuguese, for those who want, plus in English. And since my web page, our web pages at IMPA are in trouble for some time, you cannot download it from there. I'll be sending to you, okay, those who have signed up. I'll send it by email. It's big files, so I'll probably send it in parts, okay? And that's basically it for this introductory thing. So let's start talking about PDEs. So what we're going to be seeing in the beginning of the course, right, for a few weeks, is, and I'll start today, is no applications. But of course, as you can see, I like applications, so I'm going to get to it and stick with it a lot of the time. But I want to talk about PDEs in a geometrical theory that maybe it's not so clear in the beginning, but it has to do with waves. It will be clear that it has to do with waves, has to do with propagation of information, if you would like, right? In a very geometrical way, very intuitive. I find it very, very pretty. And I'm going to start with quasi-linear equations, and then I will talk about nonlinear equations. Okay? And this will be doing it for the beginning for a few weeks. And then, here and there, I'll start putting applications for us to see how to use it in an application. Okay, so let me start with something which I'll call here in the notes introductory concepts. Okay? So look at this. Let me write a super simple, the most simple wave equation we have. And these simple models many times are very useful to test things, in particular to test numerical methods. So there's this wave. If I talk about the wave equation to you, you probably will not think of this one. You'll think of another one, which is actually very closely related to this, but which appears in undergraduate books. So the one I want to study here, to start looking at, is this one. Okay, where this is the notation. Okay, partial derivatives. Let me say C is positive. And since this is an evolution problem, right, I need to put an initial condition. Let me say I call it FOH, F. Okay? So this is the first order wave equation, and what I said to you, that usually sometimes you don't even see this, because what you see, usually what we see in introductory texts is this one, right? That we learn how to solve, that needs two initial conditions. Right? And we'll come back to this and see how to find the solution that maybe you might heard of it, which is D'Alembert solution. But this one, we learn how to solve it. You probably have seen this maybe in undergraduate course. You learn how to solve this by what? Do you remember how you solve this? Fourier series, but that arises from, say, separation of variables, right? The way you motivate it. You say that u is a function of x, capital F of x, times another function, capital G of t, and then you get something that looks like an eigenvalue problem, and naturally comes out Fourier series, which is correct, or Fourier transform if you're on the whole line. Okay? We're going to come back to this. Okay? This one is very simple to solve. We can also use Fourier, whatever, but let me do it in a way which prepares ourselves to see the method of characteristics. But this is not, at first, this is not even method of characteristics. This one, we can think of this as basically solving it by inspection, which is a good exercise. Sometimes I don't like, doing magic, taking things out of the hat. Or if you do it, you then show how the magic works, right? So nothing has to be mysterious. So, so this one we can solve by Fourier series, whatever. We can solve it by characteristics too. We'll leave it this later on. This one we can do that. And this one is basically what I call and this one is the sense that waves can propagate, information can propagate in both directions. This usually when we learn in an undergraduate text, this is the equation for a vibrating string. Okay? So basically, if you have boundary conditions 0 here and 0 here, it will be a sine transform or sine series and something vibrating like this in time. Vibrating. But we're going to see this for waves propagating as well. So this one, I can do it very quickly without using Fourier series and finding the solution. Do you remember what the solution of this equation is? You don't have to remember, you'll see, but do you remember if this is the equation, this is the initial condition, what is the solution? It's okay. I mean, in a course, I love when I ask a question and you say you don't know, because then I can teach, I have more material to speak about. So this is basically, the solution is this. It's just the initial profile translating to the right with speed c, which is a constant. Okay? Easy to check, right? So if I take this solution out of my hat, it's very easy to check. It's just calculus, right? Chain rule. But now look, a little more intelligent way of guessing this. Okay, an intelligent way of guessing this. Look at this. Let me take this and let me write it like this. The total derivative of u is and put it like that. Okay? Well, of course, I'm already thinking something ahead of myself, but it's okay. But look at this, right? If I compare with a PDE, oops. Right? If I look at this, this is already telling me that if I put myself in a moving frame, then this is 0. Right? Moving frame with speed c. Right? So this is basically what's going to happen when we do the method of characteristics in a systematic way. Here I'm just playing with things that I already know, right? Taking some things out of my hat, but showing that, look, if I'm on a moving frame with speed c, then basically in a moving frame, now I'm going to read this in English, right? In a moving frame, the initial profile does not change, which means the solution is like this, right? If this is, let me call it like this, U0, the initial profile, and off it goes with speed c. It's a wave moving with speed c. Okay, so we're going to see this more systematic way with characteristics. Right now I'm just playing with things that I have in my head, faking that I don't know. So another way of also graphing this is like that. So if this is x, this is time, and this is u, if this is my initial profile, right, at a later time, it's here, and right, this angle here has to do with c, the x dt. And that's how information propagates along these parallel lines, okay? So, right, so I'm putting here in the notes, maybe not much need to speak about, but if this f is smooth, for example, C1 has first derivatives, everything is fine. In the future, I'll actually show to you that even if f is not smooth, right, even if it has like a jump, we can still make sense of things. But let's leave that alone, okay? Let's see what else I want to mention. Okay, later on, because this is not in the notes, I hope I remember, I think I will, because at some point, but since some of you mentioned you're interested in probability, I'm going to get this equation here and put this c here and ask the question. I will not give you the answer now, but ask the question. If I have uncertainty about this c, right? Let's say that c is 1 plus or minus an epsilon. I can normalize the speed to be 1. So if c is 1 plus or minus epsilon, where this epsilon here is random, right? I think the speed is 0.97. And then one of you say, no. I heard that for this wave, the speed is 1.05. No. And, okay, so it has a distribution. So how to make sense of this very simple problem if c is random and give the correct answer of the right, say, averaged wave profile. It's very simple, but you see that one can make mistakes. Let me leave it at that. That's going to take quite a while for me to get back to that, but I just want to put it here as a little bit as a teaser. Okay? Okay, propagation of information. So here, I can ask this question, which with characteristics, we're always going to be looking at the space-time axis because we're seeing things propagating, right? So I can ask the following question. If I have a point here, C, okay, and I can ask the following. What is, and I have a point, let me say, and ask, what is the region of influence of C in space-time? Right? Another question I can ask, is I have a point here, which I'm going to call capital X, capital T, and I can ask, what is the, how would I say it? Yeah. Okay, so this guy is for here. So what is, maybe, right, we can look at it, whatever. Let's look at this one maybe first. That's why I'm writing. So if I have this point xt here, capital X, capital T, and I ask, what is the domain of dependence of this point? What do I mean by that? So this problem is a problem that has initial conditions, right? This is the initial condition. I didn't use this word, but it's obvious. This is the initial condition. Things evolve in time, right? Here I did the picture, which is space-time, this wave evolving. So I'm seeing a film all at once, the beginning, the first photograph, and how the wave evolves in time. So it's natural to ask, this wave at that later time, it depended on what information at the beginning? That's the domain of dependence. For this problem, the domain of dependence of this point is very simple. It's the line that came to, so look, the domain of dependence for this wave height is exactly this guy here, which is exactly the same wave height. So if I change this initial condition and make a wave of the same amplitude, but a little wider, it does not change the solution here. It changes only on the sides. So therefore, the domain of dependence of this point, it's this point here, which is actually the same xi here, and the region of influence of this guy is this straight line, which is the characteristics that we're going to see, right? So that's normal. We're going to see that for this guy, for this equation, let me write here, let me give you just one case like this, small. If I have a point here, the domain of dependence is going to be like this because it has two characteristics. So if I change my initial data in this interval, right now you have to believe me, but I'll show you. If I change the initial conditions in this region, it will affect this point. But see, but it will affect this point at this time, right? If I have another point up here, whatever, it depends, then the characteristics are a wider, not a wider, but a bigger triangle. So this is what we're going to learn now about characteristics. Right now, I'm just giving a little bit of a propaganda, commercial of what characteristics do. They do this traffic of information, how it flows around in the domain according to the differential equation. Okay, in this case, two pretty simple constant coefficients, linear differential equations. And now, I'm going to jump into a more complicated differential equation. That's why I call this introductory concept. I'm going to talk about a quasi-linear differential equation, and then we're going to go to one that's fully nonlinear. The quasi-linear is nonlinear, but I'll explain in a second, and then we'll see what is the fully nonlinear differential equation. Okay, so let's go here. Okay, so I'm going to do a quasi-linear equation for a scalar solution, okay? And so let me put here, as I put the PDE. In free space, because I'm considering the whole line, I will not care about boundary conditions right now, okay? It's this equation. And if I'm writing too small, in particular for those, please complain, okay? Because as I write faster, I write smaller, but complain, okay? Okay, so these are partial derivatives, right? I think I'm just, since in the beginning, let me make sure my notation is clear, but you already got it. So this is a quasi-linear PDE, okay, in a scalar, which is, since U is real, okay. We'll see systems afterwards where this could be a vector, okay. Why this is not linear, why it's called quasi-linear? It's called quasi-linear because it's a first order, so let me put it here. Why it's first order? Because it has only first order derivatives. That one is second order, the wave equation, okay? First order, where it is called quasi-linear because it's linear in the higher order derivatives, but it is nonlinear in the lower order derivatives. Since here the highest order derivative is first order, right? If we've seen high order, it could have, we'll see later on, okay? It could be nonlinear. And there's one that's also called semilinear. Semilinear is when these guys are linear, but only this guy is nonlinear. The forcing term, sort of the right-hand side, if we think it's a bit of the forcing term, being nonlinear, okay? So this is called a quasi-linear equation. And we're going to see soon, not today, not next week, but maybe in the other week, a dramatic change from the geometrical aspects of solving this equation and solving a fully nonlinear PD. Let me just put here an example of fully nonlinear and put here on the top is one that's called the Aikono equation. We'll study it, which is like this. This is a truly, they're both nonlinear, but this is called nonlinear, this is called quasi-linear. And as we're going to start studying now, geometrically, there's a big change between this and that. And it's really a lot of fun, I think. It's very interesting. It gives intuition for waves, understanding all the underlying geometric. So it's very constructive and very inspiring for the intuition. So let's go. Geometrical interpretation. Okay? So this equation here has a very simple, very, very simple geometrical interpretation. Let me write a figure that might inspire you. Maybe when I saw this the first time, just seeing the figure maybe was not enough, but still, then I say something, you're going to say, oh, of course. So let me put it here. I hope this is okay for the camera also. Okay, so I have this surface, this smooth surface. Let me get here so I'm not in front of anybody. I have this smooth surface in 3D, X, Y, Z, where Z is actually where I'm going to be plotting my U. No big deal, could have called Z over there. Okay, so this surface here is called, put it here. Integral surface, because basically, if I know the surface, I have solved the PDE. Right? It's called integral surface. I integrated the PDE. Right? So this is the integral surface, because it's a surface defined by the solution. Right? Okay? No big deal. Simple geometry. Good? Now with this picture here, there's a very simple geometrical interpretation for this PDE, which will then lead us to equations which will be ODEs, it's going to look like ODEs, for the characteristics. So for how information propagates. traffics around, right, propagates around the space-time domain. Right? So with this picture in mind, this is a very simple geometrical identity. Look at this. With mathematics, right, many times you add one, subtract one, you do manipulation, you change the notation, and things start becoming more obvious, right? So let me do a simple manipulation. Okay. So this is the same. Now another simple, almost pedantic, but simple, but it helps, right? Mathematical change. This is the same as right? I'm simplifying. So this is like a surface level. Let me actually write in more detail, right? Right, this is a surface, level set 0, right, of this surface. Now, put this together with this, and you will see that this says that basically the integral surface is S. So the PD is nothing more saying that the gradient of S, meaning the normal of S, is orthogonal to ABC. Right? So therefore, ABC is tangent to the vector, to the integral surface, right? And then, from this, let's sort of use some parametrization along S. And I'm skipping some things of the notes, but it's I don't think it's any big deal. So which is little s. Okay, or say if you think of this, right, this is a point x, y. I want to do something better, and I did not do it, sorry. Can you see what I'm writing here? Sorry, it's a little small, right? I'm sorry. Let me fix this picture here, so I can still use it. So the point, right? The point P0. This is the notation I'm going to be using, the point P0. Can you see it better now? Right, so it's a point P0 on the integral surface is defined by x S0, y S0, z S0, right? So that's my parametrization. Then if I move along here on the surface, I get this ODs, and basically I'm going to get this ODs here, and the notation is going to change. At some point, I'm going to have S here. At some point, you'll see when I do the Cauchy problem, I'm going to have to use two parameterizations. Very soon, this is going to be tau, maybe tau, and actually, so I can communicate better with you in terms of intuition soon, even now, I'm going to start thinking of y as time. And actually, at some point, I'll even call it t. So the notation is going to flow around so that we can think, and I'll give you examples, of this as an evolution equation, right? Like the wave equation. This is time, right? This is some complicated speed. This might be just one, okay? And this might be a forcing term, right? And we're going to see the famous Burger's equation. Burger's equation is a famous and good first example for a quasi-linear equation. Smooth solutions lose regularity in finite time. So it's an excellent, simple example to understand things. But right now, this is the important point. Once we define the integral surface, right, which is basically just this, it's the solution, the surface of the solution. Then, if I think of this, write the surface like this, no big deal. This is the PDE. So it's very geometrical. It's just the inner product of the gradient says that this guy is tangent to the integral thing. So actually, this guy gives the flux somehow of how things are going to flow over this integral surface, right? I haven't solved the problem yet, but the geometrical picture is this. So I will need, as you will see, let's see how much time I have. No, I have plenty of time. I might start speaking, let's see, maybe not today, but next class of the Cauchy problem, or maybe on purpose I'll skip one thing and talk about the Cauchy problem, excuse me, and come back on Monday, is that this system of ODE here will have, to some extent, an initial condition for this parameter to flow, which usually is going to start at this point, P0. So I need to know what these guys are. But as we will see, right, and the Cauchy problem will become more clear, is that this is a one-parameter family of ODEs. So it really, so this might be a little fuzzy for you right now. A PDE is an infinite, if this is time, a PDE is an infinite dimensional dynamical system, right? Has infinitely many degrees of freedom. For example, just look, it has the initial condition, right? It's a function. A 3x3 system of ODE in the usual sense is a finite dimensional dynamical system, right? I have 3 initial conditions, I have 3 degrees of freedom. This guy here is not a finite dimensional dynamical system because this will become clear in a while. But it's a one-parameter family of ODEs. So it's basically a PDE dressed up as an ODE because it's simpler to do some analysis and to compute things and even to do numerics with it. Okay? That's what I want to say at the moment. Okay? So these are the characteristic equations. So these equations, we'll see an example, tells us how information flows in this domain, right? And when we see the characteristics, which I mentioned over there, in the x time plane or the xy plane, I will not, at one point, I will not make a distinction. We don't make a distinction, oh, I'm going to call it characteristic 2. But the right name is a characteristic projection, right? Because this is in 3D, and what I drew here is in 2D. So this is a characteristic projection, but no big deal, okay? Usually we talk, oh, characteristics, and if it's not clear, you should ask me, Andrea, are you talking about the full characteristic or the characteristic projection? Okay, so it's no problem. Okay. So there we go. That's how we start our geometrical interpretation of this equation. Quasi-linear equation. Maybe erase this. Okay, so now let me do something that in Fritz-John, it's actually, I'm not going to write it as a lemma, but I think in Fritz-John it is as a lemma. So let me put here C Fritz-John. I think it appears as a lemma. Proposition doesn't matter. So if I have this, this is my integral surface. This is P0. This is the point SS0. Okay, I'm going to call this curve here. This is actually a curve, doesn't have to be a straight line. Z of S. Okay, I'll explain to you in just a second what's in mind here. It will become clear, I think, now. So gamma. Is sometimes the name it's given to the characteristic, right? This is S. Let's see if I'm solving. Huh? Okay, so here is, say, the problem, or how the lemma goes. Let P0 is X0, Y0, Z0 be a point on S, the integral surface. I'm abbreviating things to make things faster here. Okay, or actually in the notes I wrote it like this. Let me leave it like this. Doesn't matter. Gamma is a characteristic curve passing through P0. So I'm going to write as a question, slightly different, written in Fritz-John is gamma entirely in S, right? In the lemma, I think Fritz-John says, prove that gamma is actually in S, meaning it cannot cut through the integral surface, right? So if gamma is a characteristic, satisfies that system, right? And it goes through the surface, right? Then it has to be on the surface. It cannot, if it's a characteristic, it cannot go through the surface, an integral surface. It has to belong, which means, to some extent, as other lemmas nearby, the same part in Fritz-John, and I'm not maybe going to talk it here right now in the course, because they're kind of simple. Like this one is also simple. It's basically almost you can think of the integral surface like a locally. You will see actually this. It's like a foliation of characteristics. Okay? So if a characteristic, again, I'm sorry I mean repetitive, if a characteristic goes through the integral surface, it actually has to be on the integral surface. So basically, the thing to do here is to look at this deviation, call it capital U, and see how this U evolves, if I think of something like time-like, right? Evolves along this curve here. And we'll see that actually U has to be identically 0, which means the guy has to be, it cannot go above the integral surface. So let's call U of S is defined as Z of S minus U of x of s, and this is 0 since P belongs to S. So here I'm using the same parameterization, or it doesn't matter. I don't think it doesn't matter, right? As we go along here. So then if we compute du ds, okay, no big deal. It's going to be chain rule. Right? From the definition. And this is going to be, let me skip one line because it's simple, right? This is going to be this. I didn't close the parentheses correctly. Let me see here. Where's my mistake? Yeah. Right? Because you pass this guy on the other side, right? So basically, all in parentheses are the same. Okay? And then, basically, we have used the characteristic equations for these guys. And basically, we will conclude, to conclude, that basically we're in this situation. In the notes, there's one line that I'm skipping. You check it on your own. Basically, we're concluding that at that point for this u, this deviation, it's a critical point. So it's 0, and it's 0, so right, it cannot go. So very simple, right? So this is just to show that a characteristic that sort of goes through, it cannot go through an integral surface. And the integral surface, sort of locally speaking, you see it's like a union of characteristics. Okay, good. So I knew I would have a little bit of time. So let me start talking about, because then I'm going to draw these things. If I'm not being clear, I'm going a little too fast. There's details, of course, in the notes. In the classroom, it's not so the best place to think about things. Let's look at the Cauchy problem, which is a generalization of the initial value problem. Okay, and then these things I think that I'm going a little maybe too fast, whatever, they're kind of simple. You will understand. So, in some sense, it's a generalization of the initial value problem, which is what we just saw. Initial value problem is that everything starts, if I think y as time, everything starts when I turn my clock on, right? From, say, time 0 or time t0, right? Then things evolve. Okay, so let me draw a picture which I think expresses best what the Cauchy problem is. In the notes, there are a few pictures, but maybe, and also in the interest of time, let me do this picture here, which I think best expresses it. Okay, so in the Cauchy problem, actually, let me, out of curiosity, who here knows what I'm talking about? What is a Cauchy problem? You think you do, but okay, you're not sure, that's good, okay, again. So it's a problem where now the data, the information, is not given to me at time 0. And when I talk about time 0, it's just because it's easier to say time 0, to be time t0, right? We're going to start everything at 1 o'clock. Doesn't have, right? So time 0 is our initial time, or t0. So now, information is going to be given to me. So information, data, is given to us along the curve gamma, which is parametrized like this. Okay, so I have this curve gamma in 3D, right? That's parameterized like this. X is f of s, blah, blah, blah. We'll see concretely problems like that. Okay, and I can actually, to give a little bit of a physical interpretation of this problem, I can project it here. Let me see if I can draw this in a good way, yeah. Okay, at least this abstract geometrical problem, it looks like it's fine, right? I have now my integral surface S, which I'm actually trying to find, but we have, for us to understand what's the structure, is like that. Now, this is the gamma where I'm going to put my initial data. Now, so I can communicate better, let's call this Y is time. Okay, so this is, right, of course, is space. And let's call this wave height. So just to give intuition for this problem, the Cauchy problem. Okay, so of course, at a given S, I am here along this curve, right? So look what this problem tells me. I mean, what it says in a physical sense. In a physical sense, it's saying, and this actually happens in reality in many problems. Say, of course, atmospheric weather predictions is much more complicated than this, but happens a little bit, at least the story is similar. Look what I'm saying. I'm saying that at x1, let me just put here, 1, 2, 3. At x1, at position 1, and time 1, and put it like this so it's not really, I was given this wave height. So I had in some place a station at place 1 that at time 4 o'clock, whatever, gave me the wave height, which was this. Some other station located elsewhere at time 2, at some other time, gave me the wave elevation there. And a third station, at some other time, gave me the wave elevation there. This is the Cauchy problem. So I have data, I have information of my wave at different places in different times. That can happen in practice, no big deal. Okay, no big deal. Now mathematically, the picture is fine. And now mathematically, right, we're going to really see now you can see probably, at least if it was me attending the lecture, when I mentioned that ODE is a one-parameter family of ODEs, and therefore it's an infinite dimensional system, not a finite dimensional as an ODE. Because look, let me erase here a little bit. If I'm at this point S, now at this point S, I have the position, the corresponding position given by f of s. S is just some parameter, right? So it gives me the position. This function gives me the position. This function gives me the time at which, at that station, I measured something. And this function gives me what I measured, say wave height, right? So now I have initial conditions. So here, right, here, I basically have x0 equal to, let me write it as f of x, y0 equal to, no, let me put this, it's better like this, sorry, something even better. Like this, it's even better. Right? I have these guys at this point here, and I have the initial conditions to solve that system at that point. So basically, this is my characteristic with information flowing out at that point now, okay? And then if I have another point, which I can call S tilde, I compute then x1 as f of S tilde, y1 as g of S tilde, z1 equal to u1 as h of S tilde. And now I have the initial conditions to solve that system again, now out of another position, and maybe this will flow more like this. The initial information. So this is one characteristic, this is another characteristic, right? But since I have an uncountable, right, a continuum of parameters, basically I have an infinite dimensional, so I have infinite degrees of freedom. That's why it looks like an ODE, it looks like a finite dimensional system, but it's not, right? It's a one parameter family of ODEs sliding along this orange curve. And as soon as I stop at a point of the orange curve, through the characteristic system, I know how to flow out of there and basically evolve in time if I'm thinking time. And actually, as you will see later on, it's actually easy to somehow locally, right, find my integral surface locally and even have a local existence theory with ODEs if things are right, the coefficients are well behaved and so on, locally, by having this sort of two system of coordinates. You're looking strange at me, and one thing you have a reason, which I didn't do correctly here, or I abused of notation here, which is this. I mean, can you see, let me ask you, for example. I'm not transferring responsibility because it's my responsibility with the notation, and I kind of already mentioned that. But I've abused of notation here. Can you see why? Because let me write the characteristic system that I'm solving. I'm sorry for this because I told you I keep on switching with S, tau, T. So let me tell you what the characteristic equation I'm solving here should be written like this. I am sorry, because I mean pedagogically what I did is not good. Okay, it's not good. And please, ask questions like you were saying. Now, please ask questions because, like I made a silly mistake last time from talking and writing. So here it is. Look, the S. So now I have two parameters, right? I have parameters. S is running in this direction, and tau. Oh, this is not good for I think for the video. And tau is running along the characteristics. And that's why I mentioned that somehow I locally have two variables that define locally here the integral surface in S and tau. You're going to see situations in which I cannot get out of the orange curve. I'm stuck on the orange curve. That's a problem. That means we have bad data. You will see why. You'll see why. But if I have things okay, everything in this direction is S, everything in this direction is tau. And I apologize because I switched notations. I mentioned that before, but I didn't point it out to you, okay? So in this problem, right, it's like this, right? now that I made the mistake, let me put things, right? And the solution of this, and this is important. I was going to fix this mistake because soon I'm going to be writing what I'm writing now, is that the solution of this, we write it like this. Right? Or I did this on purpose. Or if I want to use, this is how we're going to write it. But if I want to use a more like ODE notation, this is just for pedagogical reasons, with an ODE notation, it would be like this. Right? From the mathematical point of view, no big deal. But when I write it like that, I'm telling the reader, the audience, in a more clear and obvious way, and sometimes the notation is good for that, that this is the solution of an ODE in quote-unquote time along the characteristics, but which depends on the parameter S of where I'm starting from. So like this, you see, this is indeed a one-parameter family of ODEs, an infinite-dimensional dynamical system because it depends, right, and has infinitely many degrees of freedom to some extent. Okay? So, good. Okay. Oh, two things I wanted to mention. Very simple, but just for pedagogical reasons, and we're taping things that I want to mention. So what is the picture I can draw for a Cauchy problem, which is really an initial value problem? That's very simple, right? So an initial value problem is a very specialized Cauchy problem. That's why it's just called an initial value problem. It's where this line here is here, because time is equal to 0. You agree? That's the initial value problem. All the information was given at time equal to 0, right? And my gamma curve, therefore, my drawing is not that very good, but just put this up, right? It's there. And then our characteristics are going to flow like this. Okay? The Cauchy problem is this one, which is more complicated, more interesting, where points of measurement, times of measurement are different, right? But they have to follow certain rules. So one thing you're going to see, I don't want to rush, maybe I want to stop at a good point to come back to next week, but one thing I can anticipate, because I don't know if I have time, is that I am in trouble if you give me an initial curve, gamma, which is characteristic. Then I cannot solve the problem. Right? And you might be in trouble too, because you might give a, well, no, because if it's characteristic, if I know, no, so fine, I said something wrong. But there's other situations where we're in trouble too, which is an envelope, which is a caustic. I'll talk about this later. But if gamma is a characteristic, I'm stuck, I can't solve the problem. Well, it's kind of intuitive that, because basically, look at this, if I give you as gamma this curve here, how am I going to solve it on neighboring curves? I don't have any information. So I just have a line. I cannot construct my integral surface locally. Okay? But let's see in an algebraic way. You will see in an algebraic way why do we get stuck. It basically comes out of implicit function theorem. Okay, so another comment that's in the notes, but I don't need to write, is that in the initial value problem, right, we have basically only one initial gamma. In the Cauchy problem, to get the same solution, you can give me different gammas and we'll get the same solution. Let me put it in an application sense. For example, we're measuring something, all of us were measuring the same wave, right? But each one of us here in this room are at different places at different times, right? So you went to one place and you measured the wave there you went to 3 different places and measured there at 3 different times. You went to other 3 different places, 4 different places at different times. But the solution is the same, which basically is intuitive. So here are, say, 3 different gamma curves, which from there, they're going to generate the same characteristics. It's just that you're measuring the same phenomena at different places, different times. It's fine. For the initial value problem, there's only one unique sort of data to generate the surface. That's all the comment is, and I can see from your faces that this sketch here is enough, right? Just being at different times, different places. Okay. I think this I've already mentioned, yes. Yeah, I guess here too. So, yeah, I think let me use maybe not all the time so I can finish at a good point for next week, right? Because then we have almost a week since it's just Monday and Wednesday until the next class. So look at this. We solve characteristic ODEs and we get this. Right? Looks like we're good. But then, if we pay attention to this, well, we see that we're not quite there yet, right? Because we also saw that Z, this is the answer. This is what we want, right? And here, if I write Z as U, I have my solution given in these sort of local coordinates, not in the original coordinates. So I have to invert, I have to come back, and that's where trouble sometimes arises. Well, if I have to come back, basically I have to invert this, and I want what we want, say, is, that's in my notation, I think it's just kept on, yeah. Okay, let me switch to the notation in the notes, sorry. You're okay that I'm switching from tau to t, right? That's just my dummy variable of parametrization, okay? So this just makes a little, so if I can switch this, then I just plug. That's what we can do for the wave equation, simple wave. If I can do this switching here, I can just plug this in here, and boof, the solution is done, okay? But then the question is, can I always do this? So what we want is this. Can we always do it? Okay? So basically, it's the change of variables. Right, so that we can substitute over there. So basically, we need So since we're looking at one point, which is the point S0, so let's look at things, basically look at the neighborhood of this point. So basically, say the inverse function theorem, I basically want to change my coordinates, right, from dependent, independent, so on. Depends in this S naught being the neighborhood of P naught, right, at time 0, if we think that is at the beginning of the characteristic, right? So let me just, for those, and also for the video, so if this is gamma, S0, this is the direction of time, and this is time 0, right? If we're flowing through the characteristic. So this is what we need, so we can sort of go from, do this change of variables. And now the interesting thing is that this boils down to this. Where I'm pointing the notes that this is the data, and this is the initial ODE field, right, for the projection and so on. And if this determinant is different from 0, which comes from this is just rewriting this with a notation that comes from characteristics and differentiating along the Cauchy curve. Okay? And then I think on purpose I'll stop here, right? And basically it's a good point, and we'll see. You can think about this, and I'll send you the notes, right? For the course, right? Please do this so it makes my life easier. Send me email, right? You know my email, right? Did I write in the beginning? I don't know, but my email is okay. Send me email because then I copy paste. It's much easier, and I'll send you the notes, right, of the course. And tell me if you want both. I can send you both the Portuguese one and the English one, because there are minor differences, more towards the end, but maybe it's good to have both, because there's some differences, and depending on how this course goes, I might borrow some things from the Portuguese one, which is not written in the English one, but I'll put it on the board. It's up to you, okay? And then you will see, and I will come back to this. That's why I want to stop here, because it's a good point for me to come back on Monday, next class, is that this basically says that if my initial curve is characteristic, this will be 0. I'm doomed. I cannot invert the role that I need to then get my solution in physical space. Okay? And if, just since I have also maybe just a little bit of time, maybe let me just erase here. I'll do this afterwards, but if you want to just practice, for example, for this case, right? Solve it by characteristics. It's ridiculously easy to switch the role of S and tau to X and T, whatever, right? It's very, very simple, because the characteristics here are going to be like this. Look, let me write it. Let me write it in T. No, let me write it like this. In tau, this is going to be C. Let me adapt the notation, right? So look how simple it is with no guessing. It's good. Since I started the class with this, let me finish with this. Good. Since it's so simple, right? If I just follow the rules, the characteristic, I mean, we don't want things memorizing things, right? But if you just plug in the characteristics, dx d tau is c, dt d tau is 1, and da 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 da. So then you say, well, wait a minute, it's an initial value problem, but so look, dt d tau is 1 means that tau is identical to t. So, oh, here was already t. I did it already by mistake, right? So this means if x is a function of t, right? Because I'm following some orbit, and this says that if I do it in this moving frame, which is cx minus ct, the solution does not change. It's exactly how we started the class, with no guessing now, right? No guessing now, not thinking about chain rules and, right? It's exactly what we did at the beginning, right? So, of course, we're going to use this for more complicated problems. Okay, so good. This is a good point to finish. Obrigado.